Hello, and welcome to this short course on models of social dynamics. I am Paul Smaldino, and I am an assistant professor of cognitive and information sciences at the University of California, Merced. In this unit, we will tackle contagion. So, the basic idea behind contagion is that things spread from one person to another. Diseases for sure, but also information, behaviors, and technologies. Your friends buy a new kitchen appliance, and then you buy the same one the next week. Your cousin starts doing hot yoga, and you find yourself at a Bikram studio a few days later. The question is, what does this look like from a dynamical perspective at the population level? What is the time course of adoption? So, the study of adoption really goes back to 1962, which is when the first edition of Everett Rogers' now classic book, The Diffusion of Innovations, was published. So Rogers studied how various innovations were adopted, everything from hybrid seed corn among Midwest farmers, to the adoption of ham radio among tech enthusiasts, to the adoption of new ideas among French intellectuals. And he found that most of them exhibited a sigmoidal or S-shaped relationship of cumulative adoption over time. That is, adoption increased slowly at first, then increased rapidly, then slowed down again. What, you might ask, explains this apparently universal pattern of adoption? And so let's think about a model in which we can assign every agent one of two possible states, infected or not. This terminology is taken from the idea of disease contagion, but it can be applied to the adoption of products or behaviors if you think of infected as simply indicating that the agent has adopted whatever it is. So agents can move around in space. Sometimes an uninfected agent becomes infected. You can think of this in a variety of different ways. We could be talking about literal disease infection, but we could also be talking about the adoption of an idea, a behavior, a product, whatever. So if there's no way for an agent to become uninfected, and we can consider that later, then obviously this model is always going to end up with the whole population infected. However, exactly how that happens isn't necessarily obvious. So we'll focus here on what the model predicts about the temporal dynamics of infection based on how individuals become infected. And let's keep in mind that S-shaped sigmoid curve that Rogers found in all his studies. So how do agents decide whether or not to adopt something? So one kind of assumption we can make is that all agents have the same information about the product or behavior and make independent decisions about whether to adopt. So we can assume, let's start out with the most simple model in that all agents are the same. Right? Each agent adopts with a fixed probability. We can introduce a variable to our model that determines exactly what that probability is, the probability of adopting at every time step. So consider this. What we're really assuming here is that agents all have the same information and the same psychology, the same proclivity for adoption. And again, what we're looking for is the dynamic pattern of how they adopt over time. So let's open our model. This is contagion_spontaneous.nlogo. And we will build on the simple model of agent movement that we used at the end of the last lecture, in which we had a bunch of agents moving around randomly in space. In this model, we're going to update it so that instead of just moving around not doing anything, what they're going to do is become infected or adopt. So here is our model. And notice I've gotten rid of the pen down, pen up switch and added a couple of new sliders. One is called init infected, and that's just the number of agents that are infected initially. And then spontaneous infect is the probability of becoming infected on a given time step. I've also added a plot. NetLogo makes plotting dynamically very easy, which is one of its nice features. Oops. Let's go to the code window. What I've done here is modularize the setup and go procedures, which is nice. in terms of making the code more readable and easily transferable. So when the model is initialized, agents are created, and they're all initialized to infected being false. And then the procedure setup infected is run, which just infects whatever number we've specified. And I've just added a little check here to say if the number of infected is greater than the total number of turtles, let's just infect one. Afterward, there's a procedure called recolor, which just updates the agent's color to match their infection status. So infected agents will be red and uninfected agents will be white. So if we go back to our interface tab, set up the model, I've created 300 agents. You can see that 3 of them here are red infected. Going back to our code, I've added a little check. Going up and down. All right. At the beginning, it just checks. We check if all the agents are infected, or if none of the agents are infected, stop the simulation because either the infection has died out or it's completely saturated. Then, infect susceptibles. This is a procedure that just has every turtle with the probability spontaneous infect become infected. And it does this by generating a random floating point number between 0 and 1. And when that number is less than the probability of spontaneous infection, which will happen exactly that proportion of the time, then the agent becomes infected. Then we recolor the agents to reflect their new infection status and have them execute a random walk just as we did before. Now, in this model, the random walk does nothing whatsoever. That will change in later models. So, what does this look like when we have it go dynamically? We can start out and look at the trajectory of infection. And what we see is not an S-shaped curve, but an R-shaped curve. It's very different. This is asymptotic growth, where the rate of adoption is maximal at first and then continuously slows down as there are increasingly few individuals that haven't adopted. So what this allows us to do is confidently say that innovations don't diffuse this way, with everyone having the same proclivity for adoption and the same information. So what gives us those S-shaped curves? So let's go back to the diagram of the S-shaped curve, and now I've added on the bottom the basics of Rogers' idea. So Rogers knew back in 1962 that an explanatory theory required something more than the assumption that there was just one type of person all responding to the same information. And his proposed solution was based on the idea that there's not just one type of person. There are 5 types of people. There is initial innovators, and then early adopters, early majority, late majority, and laggards. So there's a few people that are, going to be the first people to adopt when they see a new product, and then early adopters adopt fairly quickly, and then most people kind of wait a little while, half of them adopting slightly more quickly than the rest, and then the rest of the population eventually adopts, but it takes them a while. They're laggards. So this kind of distribution, and the distribution of these different types being distributed as this blue line indicates. To make this taxonomy work, Rogers has to posit very specific proportions of the population that fall into each category. This assumes an awful lot about why people adopt and how individual differences are distributed and what those differences are. And it turns out most of those are not really justified by what we know about humans. I mean, there may be some truth that there's certainly differences between individuals, but there may also be a simpler explanation to the S-shaped adoption curve. And that is social influence. So what if instead of positing that all individuals are highly differentiated, but all respond to the same information, we instead assume that, again, all individuals are the same, right? They all have the same proclivity to adopt, but we no longer have the assumption that all individuals have access to the same information, right? What if that assumption doesn't hold? This model was first introduced in 1969 by Frank Bass, just a few years after the first edition of Rogers' book. Bass proposed, what if innovations spread sort of like diseases by exposure? What if every exposure carries some risk that this time an individual is convinced and adopts? Now, it doesn't necessarily mean that every single person has the exact same psychology, only that at the population level, it looks like that. It's sort of a Poisson process for those familiar with probability distributions. So let's return to the model. So now, the fact that agents are situated in space and moving around does matter. Right? At every tick of the simulation clock, each agent considers all the other agents around itself nearby. NetLogo makes this very easy to do. We can have an agent check all the other agents around it within some radius. So for each neighbor who has adopted the behavior, there is a fixed probability of adopting. And this probability is the transmissibility of the behavior, sort of similar to how contagious a disease is. So we have to figure out how to code this, which does require a little diving into the mathematics of probability, but not a lot. All right, so let's let tau be the transmissibility. This is the probability of being influenced to adopt by someone who's already adopted. If there's only one neighbor, we're set. The probability of adopting is tau. But what if there are multiple neighbors who have adopted? Right? Probabilities aren't additive. We can't just sum them up. Instead, what we're going to need to do is calculate the probability that the contagion doesn't spread. Right? And then we can 1 minus the probability of it not spreading is the probability of it spreading. So we need the joint probability that each neighbor fails to transmit the contagion. Because obviously, if multiple of them are influenced, or I'm influenced by multiple individuals, it's the same as if I'm influenced by one of them in this model. So we need the probability that none of them influence me. So the probability of the contagion not spreading from one neighbor is just 1 minus tau. What if I have 3 neighbors that have adopted? The probability of it not spreading from any of them is 1 minus tau times 1 minus tau times 1 minus tau is 1 minus tau to the third power cubed. More generally, with n infected neighbors, the probability of the contagion not spreading is 1 minus tau to the n. So the probability of the contagion spreading is simply the inverse. 1 minus tau to the n. Right? So again, that second term, 1 minus tau to the n, is the probability that none of my infected neighbors transmit the contagion. So 1 minus that probability is the probability that I become infected. So we now have a new model of social influence, contagion by social influence to look at. And this is called a file called contagion_SI. So this model is a version of an SI model, which is a very standard type of contagion model, S standing for susceptible, I standing for infected. So let's look at it. I'm just going to open that up. You can see that I've now set spontaneous infect to 0 and added transmissibility, which is the probability of transmission by a single individual, just as we talked about. I'm going to set it to 0.1. Set up our model again, 300 agents, 3 infected. And here, the only thing that's different is that the probability of becoming infected is no longer the same for every agent. Instead, each agent or each turtle creates a variable called infected neighbors, which is just the number of turtles that are red infected within a radius of 1 around itself. And then it uses that probability that we just calculated to determine whether or not it becomes infected through social influence. I've also included the probability of spontaneous infection also in this calculation. I'm not going to consider that in what I'm going to show you, but this allows us, and you can play around with this on your own time, to look at how these two forces might interact if they're both present. So let's go back to our model and see what happens when we get contagion by social influence. Yes. Okay, what we get is a beautiful S-shaped curve. So why does this happen? Well, in the beginning, there's not that many agents that have adopted, so most interactions are going to be between agents that haven't adopted, leading to no new adoptions. So the rate of growth is slow. As more agents adopt, the adoption rate increases because more agents interact with agents who have adopted, increasing their own chance of adopting. In the end, most interactions are then between agents who have already adopted, leading to no new interactions or no new adoptions, and so the rate of adoption slows again. And any process in which this is the case will lead to an S-shaped curve, or sigmoidal curve. So now we've got a much simpler model that shows how the nature of social influence can generate sigmoid curves. And I encourage you to play around with this model. Unlike the spontaneous adoption model, the parameters that are related to movement matter, right? Things like density and the speed at which agents move around matter a lot. I'm just going to show you just an example of just how this works. Well, actually, no. I'm going to wait. The final model, I'll play around with this a little bit. One thing that I will show you is what happens if we have far fewer agents. So let's go from 300 to 30. So here it took 140 ticks for the adoption to spread. So you might assume with fewer agents, it's going to take way less time. The contagion is going to spread much more quickly. But no, 821 ticks, much more slowly. Why? Because the less dense the population, the fewer interactions occur per unit time, and the longer it takes for the innovation to diffuse. All right, so when you think about it, it makes sense. In denser populations, contagions will spread more quickly. Okay. So the most important result, let me get back to my presentation. The most important result is that the social influence model fits the data better than the spontaneous adoption model, and does so making far fewer arbitrary assumptions than Rogers' model. It shows us how social influence and local interactions can give rise to a sigmoidal adoption curve. Okay, I want to talk about one last bit. So our model that we've worked with so far has assumed that once people are infected, or once they've adopted whatever product or behavior we're talking about, that's it, they always have it. And this is actually a fairly strong assumption, right? In terms of infection, people can recover, and then they're no longer infected. In terms of products or behaviors, sometimes the product's use runs out, or people decide they're no longer interested, or they put it aside for a while. They might give it up forever, or they might take a hiatus. Let's focus on the latter case. What happens if we let people recover or disadopt, at which point they just return to a state of susceptibility? This is called an SIS model, which stands for susceptible, infected, and then susceptible again. And we can do this by simply assuming that individuals who are infected recover with a fixed probability, called gamma, the recovery rate. What sort of dynamics does this yield? Right? So one thing you might think is, well, everyone will adopt, and then they'll recover. And then so the number of infections will go up and then go down again, and that'll be that. Let's see what happens. So we'll do this by looking at Contagion underscore SIS and logo. Just going to open that up. And you'll notice that we've added yet another slider, recovery rate. All right. This requires just one little addition to code. In the dynamics, after infect susceptibles, we've just added a new procedure called recover infected. And what that does is just asks all the turtles that are infected to recover with that probability, and then it uninfects them. What I've done here also is made sure that it only checks the turtles that are infected and red. And notice that here the agents they change their color after this stage. This ensures that an agent that is newly infected stays infected for one full turn. Okay? It can't become infected and then uninfected immediately and therefore never have the opportunity to infect someone else. Okay. Let's see what happens. We're getting a nice rise. And it stops increasing pretty much. But then what happens? It basically plateaus. It doesn't wildly oscillate. It doesn't swing way back down. It basically stays fairly consistent. It oscillates a little bit due to randomness in movement. What happens is new infections occur until we get to a point where the rate of new infections exactly equals the rate of recovery, at which point we get an equilibrium. But this equilibrium depends not just on the rate of transmissibility and the recovery rate, it also depends on the rate at which individuals are contacting one another. So what happens if agents instead move a bit more slowly? Now I've reduced the speed from 0.5 to 0.1 so that every time step they just move, they move less far. Well, now the rate of infection has gone down because agents are encountering new agents at a lower rate. I'll turn the turning angle way up. So instead of kind of moving in a fairly linear, forward trajectory, they kind of just jitter. And what happens here is quite interesting. The infection rate is going to go way down. And also you start to see spatial clusters, right? The infection or the contagion is restricted to local areas where agents are contacting each other again and again and again, sort of keeping the infection within a region where there are other areas where agents in that area remain uninfected for quite a long time. So this indicates that things like contact, how agents encounter new agents, how the structure of social networks, etc., really can have a tremendous influence on the dynamics of contagion. So, what's the use of models like this? SIS models like this can be particularly useful when considering disease dynamics, unsurprisingly. If we have estimates about things like the contact rate of a population and the transmissibility and recovery rate of a disease, not only can we estimate what would be the equilibrium level of infection if it's spread, but also these kinds of models allow researchers to estimate the proportion of the population that would need to be vaccinated to prevent the infection from spreading in the first place. And obviously, this is very important. These models can also be used for a lot of other things, modeling any behavior that spreads through social influence but isn't necessarily permanent, whether it's health behaviors like diet and exercise, or things like the spread of emotions or sentiments on social networks. So speaking of which, let's talk a little bit about further directions that other researchers have taken models like this in. So one thing is that we've assumed in our model that individuals simply adopt behaviors from anyone they contact. However, there may be good reasons for not doing that. Right? In an uncertain environment, conformity to the majority behavior could be beneficial. So do what's the most popular. Maybe sample a bunch of agents and do what the most of them are doing. Or if the value of certain behaviors is opaque, um, copying particularly successful or prestigious individuals might be a good strategy. I don't know what that person is or why that person is doing what they're doing, but they're clearly very successful, so maybe I should do what they do. Right, so there is an extensive literature that has considered the dynamics and evolutionary implications of various transmission biases or social learning strategies, and it's quite interesting. Um, a kind of subset of that is the idea of complex contagion. So the models we looked at assumed that the probability of adoption is just perfectly related to the number of exposures. Um, so if I'm influenced by one individual, I have a certain probability of adopting, and if I'm influenced by two individuals, I double my probability of adopting. But social behaviors might require reinforcement from multiple sources before they're considered at all. Like if you have a whole lot of friends and one person starts doing something unusual, it's unlikely that you're going to just immediately switch your behavior to this new one. But if a bunch of your friends all start doing it, then you're much more likely to adopt as well. So Damon Santola and others have studied how behaviors like this spread in social networks and applied these models creatively to generate hypotheses that are testable. Emotion contagion is another category of contagion. So this, instead of looking at rules for adopting, we look at the kinds of things that are adopted. Some researchers have used modified SIS models to explore how emotions or sentiments can spread on social networks. And finally, what happens if there's more than one social group in a population and they don't necessarily love each other or want to be mistaken for each other or identified with the other groups? So they might view adoption by in-group and out-group individuals differently. And there may be a bias to adopt a product or behavior, but only if it's popular primarily among members of your group and not the out-group. So in this paper, myself and some others explored how this kind of bias could affect adoption dynamics and how various parameters might influence group differences in population structure. All right, this concludes our lecture on contagion and models of contagion. Up next, opinions and polarization. Thanks for watching.